Hello, everybody. It's time to get started with lecture module 4, the official content here in video 1. Let's go ahead and jump right in and bring up the slides that we'll be covering, which you can also access in lecture module 4. So video 1 is going to be all about how planets generate magnetic fields, and we need to talk about how planets generate magnetic fields so we can talk about Earth's magnetic field, and then the area of influence in space where Earth's magnetic field is sort of the strongest magnetic field going on, the area in which of space in which Earth's magnetic field has a strong influence, what we call Earth's magnetosphere. So this video will be a little bit quick and direct. We're going to talk about the planetary dynamo, and I'll introduce how we are going to approach this with my baked potato analogy on whether or not a planet will have a planetary dynamo or not. So we have to talk about how a planetary dynamo works and then what planetary properties are required to have a planetary magnetic field. And to really hammer this in, I'm going to give you an example quiz, an example exam question that you can use to help prepare for upcoming quizzes and exam number 3 in the final exam. We'll end the video with Earth's magnetosphere, where I'll talk about the Van Allen radiation belts, and then a ever popular topic, Earth's aurorae, or the northern and southern lights. So let's go ahead and jump in with how do planets generate magnetic fields. And one of the key components for a planet to have magnetic field is that if you're talking about a terrestrial planet, you're going to need a molten core, or at least part of your core that is significantly molten. Remember that Earth's outer core is liquid iron with a little bit of nickel mixed in, but it is molten. So one of the things we have to consider is whether or not a planet after 4.6 billion years, because that's the age of the solar system, is still internally hot enough to support a molten part of its core. And this is where I bring in what I call my baked potato analogy. So we can imagine if we had a big baked potato and a small baked potato. I toss them into the oven, turn it up to 425, let those things cook for an hour, and then I pull them right out of the oven. I set them on the counter, and I'm not an idiot. I'm not going to grab them with my bare hands, but I'm going to leave them sitting on the counter, and I set a timer for 5 minutes. After 5 minutes, the timer goes off, and I have like this big russet baked potato, and then I have this little tiny red fingerling potato. If I didn't want to burn myself, which potato would I pick up? The big one or the small one? Well, the answer is pretty obvious, that the small one, being a smaller potato, would have cooled faster. Meaning that not only is the outside cooler, but the inside is cooler as well. In fact, after about 5 minutes or so, you probably have a potato that's about ready to eat. However, that baked potato is still probably so hot on the inside where if I took a bite out of the inside material, it would burn my mouth, and there go my taste buds for a week. Now everything's going to taste like sand. So we're talking about baked potatoes. Let's talk about planetary baked potatoes. So really, one of the primary factors of whether or not a planet is still going to have a molten core or not is whether or not it's a big enough baked potato, if it's a big enough planet. So the Earth is the largest of the terrestrial planets. Then Venus is the second largest, then Mars, then Mercury as the smallest. So that's sort of like lining up the planets in order of size, lining up the planets in order of their baked potato size. Earth will still have the most heat in the interior, then Venus will be about the same since it's about the same size, while Mars and Mercury, after about the past 4.5, 4.6 billion years, will have cooled down enough so they can't really have a molten part of their core anymore. They have cooled down too much. So one of the key things to take away from this, the larger the object, the slower the cooling rate. And the slower the cooling rate, the higher chance of it still having a molten core after this 4.6 billion years that the planets have been around. So why do we care whether or not there's a molten core? Well, whether a planet can generate its own magnetic field, a planetary magnetic field that it creates all on its own, it depends on two primary characteristics. One, you need a liquid conductor that is convecting within the interior of a planet. A molten metal core will do. It's hotter on the bottom, cooler on the top. That sets up the convection. It's a conductor. It's made out of metal, so electrons are flowing freely. You are driving an electric current. So requirement number one, that's where the big baked potato part comes in, because you have to be a big enough of a planet where you'll still have a molten core. Requirement number 2, you need to spin around fast enough. This is going to be what generates the coils in an electromagnet, because essentially this planetary dynamo is going to be like a giant electromagnet, and how strong the magnetic field is going to depend on the current that's going through and the number of coils that you have. So the faster you spin, if you spin fast enough, then you can actually set up this process that we call the planetary dynamo. So let's look at this in a little bit of detail. Now, the precise details are not fully worked out on this one, and it's a pretty active area in planetary science because it's pretty complicated. We are talking about generating a magnetic field on a planetary scale. So the idea of how we generate a magnetic field on a planetary scale is what we call planetary dynamo theory. So what does planetary dynamo theory state? It says that a planet will generate its own magnetic field through planetary rotation, so fast enough of a rotation, in combination with an interior layer that can conduct electricity, like liquid metal, and that it has convection occurring in it. So you have these convection cells happening in the Earth in the liquid outer core. So we have these two requirements to generate a magnetic field via planetary dynamo theory. We have the convection of a conducting liquid in the interior, our molten metal core is going to do. And we know we're going to have convection because the inner regions, this solid part of the core right here, is going to be hotter than this outer part of the core out here. So we will have these convection cells set up. Now, if you spin this thing, so it spins around fast enough, what ends up happening to those convection cells is they end up making these coils. So you turn the convection cells into these sort of convection coils. And with a liquid metal, metal has free electrons, they move around freely. So essentially, you are generating an electric current that's flowing around in these coils, which is how you actually create an electromagnet. So that in combination, the liquid metal, the liquid conducting substance that's convecting, plus the rotation to set up these coils, generates a magnetic field, just like an electromagnet does. So if you ever see an electric generator, that is also going to create a magnetic field, and these things are called dynamos. This is where all of it comes from. So how are we going to talk about this in class? Well, the numbers are not very well defined on how fast you have to spin, how large you have to be, and there seems to be, there's some compositional and other effects you have to take into account, but let's keep things relatively simple. Let's just talk about two requirements and set some limits on what those requirements are. So the first one is, are you a big enough of a baked potato? Are you large enough so that over the past 4.5 billion years, you still have a liquid metal core if you're a terrestrial planet? Whenever we get to the gas giant planets, it's going to be a different liquid metal that's doing all of this. So, are you a big enough baked potato to still have a molten core? Earth and Venus are large enough. We expect them to have molten cores. The Moon and Mars are small. I mean, Mars is half the size of the Earth. It's a smaller baked potato. It would have cooled a lot more. So we're not very surprised when we look at Mars and see that it doesn't have a global magnetic field. But we do see evidence that it does, or it did, in the past have a global magnetic field, which is going to be a huge part of our story of understanding Mars. Mercury, as we'll see, is a bit of an oddball. It does have a planetary magnetic field. It's about 1% the strength of Earth's magnetic field. And even though it's the smallest of the terrestrial planets, it has the largest iron core relative to its size, which seems to buck the trend a little bit. So what are we going to qualify as a big enough baked potato? For quizzes and exams, we can measure the size of a planet either by its mass or by its size, its radius. So I'm going to give you the numbers for, we will say that if it has at least 25% the mass of the Earth, so that would be 0.25 Earth masses, 25% the mass of the Earth, or 70% of the radius of the Earth, or 0.7 Earth radii. We'll call that to be big enough of a baked potato where you expect you to still have a molten core. Now notice that it could be these numbers or greater. So if you had something that's 2 times the mass of the Earth and it's still a terrestrial planet, then yeah, that's going to have a molten core. So this is the big enough baked potato. You want to check either the mass of the planet or the radius of the planet. And then you want to see, does the planet spin fast enough? Well, how do we measure the spin rate of a planet? its rotational period. So its rotational period is less than, say, 50 days. Now, that's not an exact number, but I'm using this number because that's about where Mercury's rotational period is. Earth is definitely smaller than that. And we will say that is fast enough to generate a planetary dynamo, fast enough to get these electromagnetic coils to turn the Earth into one giant electromagnet. So we have rotation less than 50 days, and then a mass greater than 25% of the mass of the Earth, or a radius greater than 70% the radius of Earth. And those two numbers are connected. So you can look at one or the other. And whenever I make questions, I'll be very, very clear about this. So I want to go ahead and give you an example question. So let's return to our imaginary planetary system. We played this game with, does it have an atmosphere? Now let's play the same game with, does it have a magnetic field? So which of these planets, the standard star system, BLT, Rubin, or chicken salad, do we expect to have a planetary magnetic field? And just so you're aware, ME is Earth masses. So Earth has one Earth mass, one ME. All right, so here's our planet, here's our planetary data. Before we were using the temperatures to determine an atmosphere or not. Now we have to use different planetary data. So what data are we going to be looking for? Well, we want to look at the two requirements for a planetary dynamo effect. One, are you a big enough baked potato? Are you 25% the mass of the Earth, 0.25 Earth masses or larger, or 0.7 Earth radii or larger? I'll give you one or the other or both of the data that you can use. So are you large enough? And then the second one, are you rotating fast enough? So is your rotational period less than 50 days? Okay, so now we know what data to check. We want to look at the mass, perhaps the radius if I give that data as well, and the rotation period, and see whether or not they meet the requirements that we set forth for whether or not you'll have a planetary dynamo. So these are the data that I'm going to look at, and I got rid of some of the data just to simplify the situation. So we want to look at the mass, and then we want to look at the rotational period. So let's go through these and see how it plays out. So if it satisfies a requirement, I've colored the planetary data green. If it does not satisfy a requirement, does not meet a requirement, I've colored it red. And all it takes is you have to have both. So if you see any red if it does not meet any of the requirements, it does not have a magnetic field. So we can go to planet BLT, its mass. Oh, it has one Earth mass, big enough of a baked potato. Check. Rotational period, 22.3 hours. Okay, that's faster than Earth. That's another check. So yes, we expect BLT to have a planetary magnetic field. What about planet Rubin? Okay, let's look at the rotational period first. 26.2 hours, less than 50 days, that's a check. But its mass is only 20% the mass of the Earth. That's too small. We would expect that if all things are the same, this is a 4.5 billion year old planet, its core would have cooled and solidified and no longer be able to generate a planetary magnetic field. So we don't expect Rubin to have one. What about planet chicken salad? Its mass is 2.5 times the mass of the Earth. That's definitely big enough to still have a molten core. But then let's look at its rotation period, 97 days. It's a really slow rotator, too slow to set up those coils that are required to generate the dynamo effect in a planet. So we do not expect planet chicken salad. So if you're given this data and these planets, you would only select planet BLT as the one having a magnetic field, or most likely to have a magnetic field. So now that we know how planets make magnetic fields, let's actually take a look at Earth's magnetosphere, Earth's magnetic field. So magnetosphere is a new term, and pretty much the name says it. It's the sphere where Earth's magnetic field is important. So it's the region around the Earth dominated by Earth's magnetic field. And this is actually a crucial thing that makes it so we can have life on Earth. No magnetic field, we would all perish relatively rapidly, because then we would not be protected from the solar wind, we would lose our atmosphere, and we would be bombarded with high energy particle radiation, which would sterilize the entire surface of the Earth fairly rapidly, especially once we eroded away our atmosphere. So thank you, magical, actually scientific force field. What kind of force? Magnetic force field that protects us from the solar wind. So We have this cosmic force field, a magnetic field, a shield made out of magnetic field lines that's protecting us from the solar wind. What is the solar wind? Well, the sun is constantly giving off a stream in all directions of charged particles, mostly protons, also called hydrogen nuclei, and electrons that are streaming out in all directions away from the sun. Now, how much of these things are coming off, what is the flux of protons and electrons, depends on what kind of solar activity is going on, but it's ever present, so there's always a solar wind. And it's going to be streaming through space, and it's going to be, since they're charged particles, that electric part, the electric charge, will interact with a magnetic field. And that means that these charged particles will interact with our magnetic field in such a way that the Earth acts as a shield. So here comes the solar wind. It's going to hit Earth's magnetic field, represented here, so you can see these magnetic field lines. And since they're charged particles, the charged particles will want to follow magnetic field lines. That's how electromagnetism works. So the solar wind is going to be deflected around the Earth, protecting the Earth from the solar wind, keeping our atmosphere in place so it doesn't get blown away by the solar wind, and keeping us safe from all these high energy particles streaming off the sun. So thank you, magnetic field of the Earth. Thank you, Planetary Dynamo. You are making life possible. Now let's take a look at what Earth's magnetic field looks like. What is the magnetosphere structured like? And we'll take a zoomed in view first. And the easiest way to imagine this is a bar magnet. So go ahead and look up what a bar magnet looks like. Look up bar magnet and iron filings, and you will be able to see the magnetic field lines and the iron filings around it. And essentially, up close, Earth's magnetic field looks like it has a giant bar magnet stabbed through it, where you have the North Pole, magnetic North Pole, and the magnetic South Pole. Notice those are not the same as the geographic North and South Pole. In fact, they are offset from one another. And details you don't need to know, but if you're drawing magnetic field lines, they always leave the South Pole and loop around into the North Pole is the direction that you draw them. And you have basically the magnetic field that you'd expect from a bar magnet. Now, if you zoom out and look past where it just looks like a bar magnet, you still have magnetic field lines. Here comes the solar wind streaming in, and it's going to push against Earth's magnetic field, scrunching up these field lines, kind of compressing them, and then creating, just like water, when it encounters a rock in a stream, will bend around it and form sort of a teardrop shape. The solar wind will bend around and create a teardrop shaped magnetic field over on the side away from the sun. So you have this sort of teardrop shaped magnetosphere around the Earth. And the same is expected for all the planets because the solar wind is pervasive throughout the entire solar system. Now we can talk about some effects this actually has that we might want to know about, whether just from scientific curiosity, or we're trying to keep astronauts alive, or trying to position our satellites where our satellites can function without breaking. So let's talk about the Van Allen radiation belts. You maybe have heard of these. Astronauts need to go through this if they're going, say, to the moon. And we want to limit the amount of time that they're going to go through them, because the Van Allen radiation belts are these two donut rings. So you can see the Earth down here. It's just a schematic, and you can imagine these spun all the way around, creating these two donut-shaped rings that are full of charged, trapped solar wind particles. So a lot of particle radiation. This is above the Earth's ionosphere, so not within the atmosphere. It's above that. And closer to the Earth, we have the inner Van Allen radiation belt, and then further away, we have an outer Van Allen radiation belt. Well, how are these particles getting trapped there? And why do we have two different belts? So here comes the solar wind. Protons are going to have a certain amount of energy associated with them. The electrons have a different energy, charge, and momentum associated with them. They're going to hit Earth's magnetic field. At some place, as they push into Earth's magnetic field lines, they might end up hitting a magnetic field line where they have just the right energy, where they get trapped within the magnetic field lines. And that will form, say, the outer Van Allen radiation belt. And then The ones that the protons, which have more momentum, can penetrate further in, can create the inner Van Allen radiation belts. So these particles get trapped here in these radiation belts. And why do we care about this? Well, if we wanted to send an astronaut through these and there was a high level of solar activity going on, then there would be more charged particles in the Van Allen radiation belts. We'd want to make that journey as quick as possible to reduce the total amount of radiation that they're exposed to. We also do not want to park satellites here because those charged particles will ruin and destroy the satellites. So they will also destroy any electronics. So these are just things that we need to be aware of from a technical and a safety standpoint. Plus, it's just cool science. Now, let's talk about the other really cool effect. So here we have the solar wind coming in. It can trap the particles, having our outer and inner Van Allen radiation belts. But some of these charged particles, the solar wind particles, will end up hitting and traveling along the magnetic field lines. Because a charged particle, if you have a magnetic field line, let's go ahead and represent that. Here's a magnetic field line. Then a charged particle will spiral around magnetic field lines. It's just how the science works out. If you're interested, take a course in electricity and magnetism. But for now, just trust me that that's how it works. So some of these charged particles are going to get trapped by magnetic field lines, and they are going to travel down the magnetic field line until they interact with Earth. The magnetic field lines converge around the magnetic poles, so all these charged particles will come crashing in at the magnetic poles. They'll form a ring because it's really hard to come straight down. And you're going to be coming down at one of these. So you'll have this ring where you have the solar wind particles crashing into the ionosphere and the upper atmosphere. Now these charged particles have a whole lot of energy. So as they come crashing through the upper parts of the atmosphere, they'll interact with the molecules and atoms there, get their electrons all excited, strip them away, or at least put them in higher energy levels. And then those electrons get back together with their molecules or their atoms and fall down towards the ground state. They're going to emit light, and that light that's emitted is what we call the aurora, the northern lights and the southern lights. Around the northern pole, you'll have this ring of materials. More solar wind activity, the ring gets pushed further south and is larger, less solar wind activity, and it's more concentrated around the magnetic poles. But the northern lights have the official name, the aurora borealis, the northern lights. And then you'll have the same thing at the southern pole as particles stream their way down this way. So you have the southern lights, or the aurora australis. And this brings us to a really cool core planetary concept that was the subject of the picture of the day today. So if you're a planet that has a pretty thick or a substantial atmosphere like the Earth does, and you have a pretty strong magnetic field like the Earth does, then you expect that planet to have aurora. So that's why if you look at Jupiter has a very strong magnetic field, Saturn has a very strong magnetic field, Uranus and Neptune have strong magnetic fields, you expect them to have aurora. Mars has a thin atmosphere and no magnetic field, so it doesn't have aurora. And I want to go ahead and end this video by showing you just how beautiful the northern and southern lights are. So if you ever get the chance, add this to your bucket list of things to do. Go see the northern lights. It's on my bucket list. I've tried to go see them, but I went too far north. I didn't even know that was a thing. But what I ended up doing was going too far north, so I was outside of this donut. So I couldn't see the northern lights from where I was. But that doesn't mean I'm not going to give up trying, because they are absolutely fantastic to see with. Let's start with the space-based views and then go down to a ground-based view. So this is a NASA image from a satellite that's very far away from the Earth, the IMAGE satellite. And here you can see Antarctica, and here you can see the southern lights, the aurora australis. So you can see that ring going on. So you're really mapping out something about Earth's magnetic field right there. And if you are over here or over here and looking in those directions, then you could see the lights. I'm guessing during this picture, McMurdo Station in Antarctica was getting a great southern light show. Here we have Scott Kelly in the International Space Station. You can see part of the International Space Station there. And here you can see Earth's atmosphere. And you can see the northern lights here. As you can see that I have green colors, pink colors, red colors, purple colors, all depending on what kind of atoms you're dealing with and the strength of the solar wind. You can see these pillars, which will form curtains when viewed from Earth. But these pillars right here, you're really seeing the magnetic field lines of Earth. And then your ground-based view, so if you want to just do pretty short exposure photography, you'll see this, and you can see them with the naked eye, and they're sort of fluttering around. They're usually called curtains. You can see them actively changing in real time. So here are some the northern lights that you can see over Canada. And I think that's the case for both of these. I just want to show you some pictures of these. I really want to go see those, and that's one of my photography projects. All right, so I believe this is going to be one of the longest videos of the lecture module. Thank you for hanging in, and I will see you in video 2.